So in this circuit, this switch opens at t is equal to 0. We need to find the expression for this transient current through the inductance. Now before t0, this switch was closed, so of course this resistance was shorted out, 30 ohms resistance. So the steady state current before the switch was opened was something like I can write II, which will be the initial value for t is equal to 0. So before t is t cannot be less than 0, so before the switch was opened, I can just say, so that will be 100, the steady state value, so we can ignore the inductance, 10, so that will be 10 ampere. And after t is greater than 0, we will have the differential equation. I will just write the differential equations. V, so di dt L, this is the drop across the resistance, plus R I is equal to V. Now this R is of course 10 plus 30. Since this one is open, this resistance comes into play, and this one, so 30 plus 40. So this expression becomes R over L I V over L. Now for this sort of differential equation, there is an excitation on the right hand side, so the natural response is, without just the standard method for solving such differential equation, is this one. The solution will be the natural one, and with the excitation we will get the forced one, which something has to be assumed. So let's do the natural one first. So I natural, I will write, will be, since there is an excitation on the right hand side, if there was 0 on the right hand side, we will just get this one. So this one will be I e to the power minus R over L t. This one we don't know yet. We will find it from the boundary condition later. So this is e to the power, R of course is 40, so I will just leave it like that for the time. And the forced response will be, it is this part, will be of the form a constant value. So we will just assume that the IF will be, forced one will be A. So this is becoming DIF dt plus R over L IF is equal to V over L. Now since this one will become 0, since IF is a constant value, and we are assuming this to be constant since the excitation is a constant. This is a DC voltage, the excitation is a constant, so we are assuming the force response is also constant. That's what the way to solve such differential equations. So this one is becoming 0, so IF is becoming V over L here times L over R. So basically V over R. See how the L got cancelled and we got the response, which should be only dependent on R. It's coming from mathematics as well, but that's what will happen here, has to happen here, since in steady state condition the inductance is of no use. So basically the total solution will be this one plus IN plus IF. So if I erase this part, this one is no use, so this is the natural solution plus this one. So the total solution will be, I'll probably erase this whole thing. So I will be I e to the power minus R over LT plus V over R. So of course I we don't know yet, e to the power 40 over 0.5 t, that's a negative, plus V is 100 over this R is again 40. So I e to the power minus att, it's a big one though, so very 2.5 I. Now at t is equal to 0, we have the boundary condition I is 10 ampere. So I is equal to 10 I plus 2.5. Since this part is becoming 1, so I will be 7.5. So our solution is becoming 7.5 e to the power minus att plus 2.5. This is the solution, and if we plot this one, this means that initially the current is 7.5 and after the switch is closed, so it will be something like this. If we plot it, sorry, so this is when the switch is closed, T0. So this was 7.5 ampere, then the current decreases and it becomes at t is equal to 0, current is from this one, t is equal to 0, I is 10, and when t is equal to infinity, I will be, this part will be 0, so this will go away, so I will become, this I, sorry, it's lowercase I, will become 2.5. so 10, and then it will go very sharply because our R over L is very large, so it's just the selection of the values, that's why it's so large. But anyway, this one should go down even more, so this is 10, and finally it settles to 2.5. So that's it.